Good afternoon, everybody, and welcome to this month's IQ Academy webinar. Thank you for taking the time out to join us on our bite-sized session this month, which will be taking a look at geotechnical assessment with David Jameson of GWP Consultants. Webinars are aimed at helping support you and develop your knowledge on key issues within the industry, and so your feedback is really important to us on these. If you have a chance to complete the short questionnaire, which will be brought up at the end of today's session, it'll be very much appreciated, and we can help ensure we continue to keep these relevant to your needs. Time permitting today, we will try to answer any questions that we receive through. You'll be able to send these through on the questions panel, which should be to the right of your screen. If we don't get a chance to tend to any of these, we will ensure these are addressed in the follow-up materials after the event. For the next couple of months, our upcoming webinars, we have Dealing with Change with Adam Daniels from Sibelco and Landscape and Restoration with Simon Higson from SLR Consulting Limited. You can register or find out more information on these by visiting the events page on the IQ website, and the address is just to the bottom of the screen there. Our branches are also running a selection of events over the coming month. Details are available on the current slide. For further information on these, if you contact your local branch secretaries, and the contact details for those are on the branches page of the IQ website at quarrying.org. And now I'll just hand you over to David Jameson.
Well, thank you very much. Good afternoon, everybody. Thank you for the invitation to talk today. My name's David Jameson. I work for GWP Consultants. We're a consultancy giving advice on the design of excavations and tips, and we've worked to do the designs on many of the largest excavations and tips across the country and many abroad as well. Today's subject is the importance of geotechnical assessment. It's a very wide-ranging subject, and I didn't want to go too much down the road of just quoting the regulations at you, although there is some of that. I wanted to essentially show you lots of photographs about illustrating things that might have gone wrong or what to look out for when you are doing inspections, in order to illustrate the sort of things that need to go into a geotechnical assessment report. Just to start off with, there's a few photographs at the bottom of this slide. In the middle, I'm showing a photograph of a bench which has toppled out towards an excavation, showing very nicely the back scars of a number of toppling blocks. And this instability has occurred following collapse of old workings in the chambers below. And those collapsed pillars between chambers have occurred because of rapid dewatering, resulting in loss of or movement in supporting fill below, which has a consequential toppling effect on the chambers below. So always when we're doing geotechnical assessments, we need to consider what lies below the site foundations of any excavation or tip. On the right hand side there's a slide showing cracking and a hole development in a lagoon. I'll come back to that later on. And then also integral to geotechnical assessment is the need to pass on any design criteria that come out of designs into your tip and excavation rules. So the need then for edge protection and having excavation rules that prevent you from going too close to the edge. So the outline of today's discussion, I'm going to start off with what the definition of geotechnical assessment is in terms of how it's set out in the quarries regulations. I'm going to look back at the origins of the regulations, look at a couple of large instabilities which occurred, and try and derive from that the important aspects for design out of those. Consider what goes into an adequate assessment and how it's linked to other areas of the regulations. The regulations themselves are well set out and flow quite nicely, but there are sections of it split up throughout the regulations that interact quite nicely, and I'll look at how I see those interlinked together. We'll look at some further examples of instability to discuss the different input or the different mechanisms of failure and what we need to consider in any design. And then I've got an example of time permits of what goes into a design right at the end of a tip. So I'm going to deal with the definition of what a geotechnical assessment is first of all. That's dealt with under Regulation 33 of the Quarries Regulations. It means an assessment carried out by a geotechnical specialist, that's somebody with relevant competence and experience, identifying and assessing all factors liable to affect stability and safety of a proposed or existing excavation or tip. And that means for any quarry, all excavations, solid tips, stockpiles, spoil heaps and lagoons need to be assessed. Essentially, a Regulation 33 report, a geotechnical assessment, is dealt with, or what is required for that report and the basics of what goes into it is dealt with under Regulation 33. It includes details and particulars as set out in Schedule 1. I'll go through those in just a second. It needs to state the conclusion of the report as to the safety and security of whatever structure you're talking about and whether it comprises a significant hazard as defined by the quarry's regulations. It needs to say whether any remedial work is required and what timescales it's required by, and also what the date for the next assessment might be. Also, it needs to review tip and excavation rules in order that any design requirements that come out of your design go back into the rules to make sure that any structure or excavation or tip is built according to the specification. Under paragraph 2 of Regulation 33 is a requirement for the operator to ensure that any remedial works set out in the report are enacted by the required date. So just going back up to the top there, what you need to have in your geotechnical assessment report is set out in Schedule 1. It requires you to have a site survey, this is an up-to-date survey, an accurate plan of what's going on site, the boundaries of the quarry, and any structures that are significant on it, the site of any excavation or tip that's proposed, any off-site areas which might be, or contiguous with the site, which might be impacted upon if there was a failure on site. It needs also to consider any old mine workings, buried quarry workings, cave systems, and anything in the foundations which might cause an issue with respect to stability. In the report, we need to also consider data arising from any site investigations. That's not just drilling to work out where your mineral is and perhaps where your overburden is, but also things like geotechnical testing, which might tell you the strength of materials, data from boreholes, piezometers that tells you perhaps what the groundwater conditions are in whatever structure that you're dealing with also. We need also to have cross sections based on these site investigations, plans based on the site investigations as well, that show you the depth of overburden, where any weaker materials might be, that sort of thing. We need to have a section on any assumptions made before analysis, what the factors of safety might be, why they've been derived. Following some analyses to say what your design structure might be, or the design of the structure might be adequate, we need to include those and have out of that some design criteria against which the excavation or tip is going to be designed, constructed and operated against. So they are the things that need to go into a Regulation 33 report. I'm just going to jump back now a little bit just to have a look at the legislation and how that's grown and talk through a couple of large instabilities that have occurred in the past and the things that we need to consider in any design. The most infamous example of a slug failure is the Aberfan Tip 7 instability, which occurred 51 years ago or so in 1966, which killed 144 people, mostly children, when a large high face of a colliery spoil material failed as a flow slide and engulfed not only the school at the bottom of the hill where quite a number of children were resident, but also houses higher up and farm buildings higher up as well. This essential large tip failure resulted when the loose tip materials, which were being tipped over the face, failed as a consequence of a tipping directly over a spring, which increased pore pressures. The foundations of the tip were on a soft clay foundation, so we need to obviously understand what is the foundation conditions itself. It was being tipped over what was a pre-existing failure, so movement had already occurred, which might have further reduced the strength of the foundations, and tipping continued to occur even following initial movements. Essentially, what the panel found when they did an inquiry into this was that there was no design or thought gone into the tip requirements at all. This failure led on to the Mines, Tips and Quarries Act of 1969 and the subsequent regulations in 1972, which imposed standards on the constructions of tips and lagoons, but not necessarily excavations. This next slide shows the failure which occurred in 1988 at St Aidan's open cast site, just south of Leeds. Some of you may remember this. It was an extremely large slab slide which occurred as a consequence of a number of factors. And the strata here was sub-horizontal, so fairly flat, and movement occurred because of the presence of a weak shear, pre-sheared horizon, which was only a centimetre or two thick, just adjacent to one of the coal seams. Old workings from deep mine workings in the past had resulted in a strain zone at the back of that slab, coincident with a number of faults. And once water had got into these faults, it heaved the whole 1.62 million ton slab into the open void of St Aidan's and caused a mass flooding of that site at that time, and caused the river to flow backwards and produce a 70-metre deep lake in the matter of a couple of months. It was that failure that led on to some of the research I did for the coal board back in 1990 or so, essentially on the position and strength and character of these weak shear zones that lie at the bottom of coal seams, or adjacent to coal seams, sometimes at the top. But that disaster, or that failure, led on to the Open Cast Code of Practice for slope design, which was the precursor to the Quarry Regulations 1999. So these regulations have been in place since 1999, and whereas traditional approaches to slope design often were reactive and followed an incident, and thereafter involved subjective evaluation and inspection of the incident by staff with variable experience, what the Quarry Regulations set out to do is impose a framework of hazard appraisal and risk assessment to highlight where significant hazards are, and then have a proactive approach to design. So when it comes to the what I'm talking about today, which is the design of excavations and tips, these are dealt with under Section 6 of the regulations. This slide tries to pull together how I see the regulations in this area ought to be interlinked with other sections of the regulations. So at the heart of all of this is Regulation 6, which is the general duties of the operator, which requires that all structures on site are designed appropriately. And when it comes to tips and excavations, they're dealt with in Part 6, and that's the relevant regulations are sort of highlighted in that box with a dashed edge. Regulation 30 deals with the design of excavations and tips, and essentially says that they need to be designed, operated and maintained to ensure that no movement occurs which might have an impact on health and safety. This is achieved through appraisal and assessment. Every structure on site, that's any excavation or tips including solid materials and liquid materials, have to be appraised under Regulation 32. And once they've been appraised, if any of those are seen to be significant hazards as defined by the regulations, then you need to do a geotechnical assessment. And that assessment report, I've been through what you need to address in those. And linked to that, of course, once you've done your design, you need to get that back into the essential details into your excavation and tipping rules. That's held under or detailed under Regulation 31. Once you start to build or construct your structure, you need to inspect it properly, and people need to be adequately trained to know what they're looking for. So a lot of the time after I've done a geotechnical assessment, I go back to site and spend some time with the people who are going to be constructing it or inspecting it to make sure that they know what they're looking for. And not only that, we also got to consider or build in the design of benches and haul roads to make sure that they're going to be stable in the long term. And it's an integral part of slope design. So now I'm going to look at a number of different examples of things that might have gone wrong on site, just so we can hopefully highlight the different conditions, the things you need to think about when you're observing failures, and also what needs to go into a Regulation 33 report from a design point of view. Following the Aberfan failure, the regulations required that tips had to be designed and constructed in a certain way. There was a lot of work back then to put right numerous tips which were failing in the past. And the next example of the largest slope failure that I'm aware of is that occurred in the Hatfield Colliery, another colliery tip, which occurred adjacent to the Main Line Railway in 2013. It's probably significant that this occurred some 30 years or a generation later than the Aberfan failure, and it's possible that some of the lessons of the past have been forgotten, perhaps. So this large slope failure occurred in colliery discards, which is essentially a reasonably strong material. But the failure, which is a biplanar failure, essentially occurred because of the presence of laminated clays in the foundations, the presence of which had been known since the 1970s, but hadn't been included in more recent geotechnical assessment reports, and the high water tables within the structure caused by the tipping of saturated fines behind an impermeable compacted containment spoil bank at the front, and the lack of the introduction of any poor pressure relief or drains within that structure. There's an example here in a hard rock quarry of an example of some poor slope design, a lack of understanding by the designer, I feel, in trying to make this excavation work in the first place. You can see here the strata dip is fairly steep. It's about 35 degrees, which is steeper than the angle of friction. There's been an attempt to excavate the low wall upslope to create the initial box cut, but in doing so, it's undercut the strata in the face, and you can see a number of slabs beginning to slide out. In the initial design, when it was reviewed, there was an attempt to rotate the excavated faces by 20 degrees, which all the books say help to preclude planar failure, which is occurring on the back wall here. But once you expand your excavation more than about 30 or 40 meters wide, then the presence of other fault structures, some of which you can see on the left-hand side, means that slabs will begin to fall out. Not only was it a poor design, but actually when it came to actually implement the design, the excavation wasn't set out properly and excavated properly, such that they had a straight face across the back of the excavation, and inevitably material was going to fall out. And you can see on the right hand side some very large slabs of material falling out, which would have dwarfed and crushed the excavator. So not only was it set out poorly, but the design requirements hadn't been translated into the tip and excavation rules, and the guide working on site weren't aware of what these were, the limits of the excavation design, and what the failure mechanisms might be. I wanted to also show that it's important to do appropriate designs for sand and gravel excavations. There's an example of a fatality which occurred following the collapse of a haul ramp being installed on an oversteep, deep slot formed in sand and gravel. Here, there was no design for the initial excavation. There was some loading of the crest of the excavation by the dozer as it was pushing down a ramp and running parallel to the side of the face. So a lack of understanding as to how slope might fail, and poor translation of possible failure mechanisms into the tipping excavation rules. I'm just hurrying this up a little because we're going to run out of time. Here's what to look for when you're considering lagoon construction. We're not just dealing with water or silt, but any other materials which might flow. On the right-hand side, there's an example of a peat lagoon which has failed into a void due to inadequate bund construction. On the left-hand side there, you can see an operating lagoon which is beginning to fail. In the background, adjacent to the spillway, there's a number of cracks beginning to develop because of essentially the slope angle is too steep for the materials it's being constructed out of. But more worryingly, there's a circular void beginning to develop at the near end of the photograph there, and that's a consequence of internal collapse of the lagoon from internal erosion and piping out of fine materials from the slope. So whenever you're looking for lagoons, you want to be looking out for cracks, circular depressions, bulging of the faces, seepages out of the flanks, especially if it's carrying fines material. All of this information should be translated across into your tipping excavation rules. I've got a number of examples of poorer practice shown here. A lack of edge protection for tipping, lack of clear rules to make sure that where dozers are maintaining edge protection, there has to be sufficient height in them. Perhaps tipping close to the edge of tips shouldn't be allowed in any of these cases. And if a dozer is there, then it's well capable of pushing material for 4 or 5 meters beyond the edge. Right in the bottom right-hand corner, there's an extreme example of inadequate bench width, in that the excavators tried to track out, and there's been no edge protection and loading of the slope, and the excavator's fallen over the front of the face. So I don't know where we are for time. I'm going to go through very quickly last few slides just to show what considerations you have to put into any particular design. The geotechnical assessment requires, when you're constructing or considering design, an understanding of the final and fundamental requirements. What are you actually going to be constructing? How long is it going to be there? What's downslope? What are the risks associated with the positioning of a hazard? There might be a high risk or higher risk of positioning it above a school rather than in the bottom of a tip, in the bottom of an excavation. We need to consider any foundation preparation, what needs to go into that, what you're actually putting a structure on, what the ground and surface water controls might be, what are the likely pore pressures that are going to be building up within the tip, both during construction and in the longer term. We need to have a good understanding of what the materials are that are going to make up a slope and how to design, or what the strength of those might be, in order to adequately assess what is going to be suitably secure for the long term. And not just for the long term, we also need to consider how it's going to perform during construction. When you're tipping, for example, very fine materials, clays, if you build up a slope too quickly, internal pore pressures don't have a chance to dissipate very rapidly, and therefore you can get high water pressure induced failures, and therefore you might need to build into whatever tip you're designing some pore pressure relief drains. So once you've finished your design, you must also include into it suitable plans and cross sections to show how it's going to be constructed, give guidance on construction techniques, and that's got to make it back into your tipping rules, so the person doing the design of the structure should have sight of those tipping rules, so you can add whatever design criteria come out of the analyses. And I would also suggest that we need to have an input into inspection schedules as well. I'm just going to show you this very quickly at the end. Here's a tip being produced in the bottom of an excavated void. Any geotechnical assessment report's got to show a number of plans showing how these is going to be constructed, and there's just two there that I'm showing in the bottom of this void. First of all, how it's going to be, how the foundation is going to be prepared, removing any weak materials, for example, putting in a drain at the bottom, considering any speed of construction. In this particular case, we're putting fine materials in the bottom, so we have to install a number of pore pressure relief drains. In the bottom left-hand corner is the ultimate tip design. Also, we need to be cognizant of serviceability. How are we actually going to get onto the tip in the future to make sure that if there's any remediation that needs to be done, it all remains accessible. So a number of plans are required to show how the tip's going to be constructed, but also included in that has got to be, is it practical to construct it to the final design? So a number of snapshot views of what's going on are required to show you how you're going to build it, and are you going to have access to the slope at all time. Plans need to be shown, and cross sections also, to illustrate how that particular tip might be designed. Again, you can see at the bottom, we've got a number of drains which are required to address any pore pressure increase, or rapid pore pressure increase, or flooding of the void in the later date. And at the bottom, obviously, you need to do a stability assessment. Just one last slide to finish off. I've talked about it already, but once you've done your design, you've got to get that information back into the tipping and excavation rules to make sure that everybody who's working on the construction of the tip needs to know how it's going to be constructed properly, where any drains are going to be, what the compaction requirements need to be, to make sure that it's built to the required specification. Just a couple of photographs there to show, or a photograph to show this tip being constructed in the bottom of the quarry. So I think I've taken enough of your time. Thanks very much for your attention.
Thanks, David, and thank you to everyone who took the time out to join us today. As with the previous session, we'll be making a recording of the webinar and slides available for you to all access. If you keep an eye out for an email from us next week with the respective links in there. And if you do have chance, would be grateful to get your feedback of today's session on the questionnaire that will be coming up shortly. And again, don't forget to register for our upcoming webinars that are of interest. All of the details are available on the events page of the IQ website at quarrying.org. Thanks again and take care.